Okay, the next sample problem we're going to look at is going to be sample problem 2.5. Now, sample problem 2.5 is going to deal with the illustration that we see here on the left-hand side. And it says we want to determine the magnitude and the direction of the smallest force F that maintains a 30 kilogram package shown in equilibrium. Okay, so what force does it take to just keep that in place right there, static equilibrium? Note that the force exerted by the rollers on the package is perpendicular to the incline. So you can really think of those rollers as just a regular flat surface, and then we're going to have a normal or support force that's going to support that, okay? So directly down below here, and we'll look at this illustration, and then we'll draw the free body diagram. So right now you're going to notice here we have our block. Now going through the center or the geometric center or the center of gravity of that box or block is going to be the weight of that block. Now we're given right now the mass. So we're gonna have to calculate the weight by taking mass times gravity. And since we're in the metric system, it's gonna be 9.81, okay? So you're going to notice that they calculate that there, and we'll show that in our calculations as well. So one of the forces acting on this block is going to be the weight. The second force that's acting on the block is going to be that force that is pushing up to keep it in equilibrium. So it's just keeping it in place. It's not pushing it up the conveyor. It's just keeping it right where it's at so that it's in a static state of equilibrium. It's not moving. And then you're going to notice that there's a third force here, not as obvious. These two, weight and the force that we're going to be actually exerting on it, external force, makes sense. But this is going to be the normal force or the support force that this particular block is going to see. Now, a support force is always going to be, for instance, if I have a horizontal desk like I have here and I set my books down on it, there is a support force that is holding it, if you would, based on the fact that the weight is going down of my book, and then the support of that table is pushing back up on it, okay? But it's going to be in the opposite direction, but the support force is always going to be perpendicular to the surface it's riding on. So if I'm horizontal, perpendicular is vertical. But if I'm at an angle, we have to be perpendicular to the surface it's riding on. So that's why you see P as the support force here, as the, at an angle. Now, how are we going to simulate this? We are not going to do the problem like they did in here. We're going to use rectangular components. So what we're going to do is we're going to draw our axis system, and we're going to show how each one of these is then going to kind of meet in the middle. Okay. So sample problem 2.5. And before we do anything, we're going to put our convention in the upper right-hand corner. Okay. Now, we're not going to draw the block. We're going to draw a simplified version of, all right? And we're going to start with, this is going to be our free body diagram. We're going to start with an X and Y axis. And the middle of that X and Y axis, where everything comes together, is the center of gravity of our block, okay? So right here is the center of gravity of our block. Now, you can sound really fancy tonight when you go home or tomorrow when somebody asks you, what'd you learn in school last night? You can say, I learned about the principle of transmissibility. They're going to like, wow, that sounds amazing. Like you are so smart. So the principle of transmissibility is really not that big of a deal, but sounds good. Kind of like the Pythagorean theorem. Like, oh, it sounds really smart, right? So the principle of transmissibility says that I can move a force anywhere along its line of action, and it will have the same net effect on the body, okay? So what that means to us is, for instance, I can move my weight anywhere vertically along that line, and it's still going to either push that block down, or if I'm pulling on the bottom of it, it's still going to go in a downward direction, whether I push it from the top or pull from the bottom. So we are going to show our weight going straight down, coming from that center, okay? So the weight is going to go straight down like this. We're not going to do it from the top. We're going to have the tail is going to start at the origin and it's going to point down. And we know this to be the weight. We'll calculate the weight in a little bit, what its magnitude is. The next one that we're going to do is going to be this F force. This F force you can see from horizontal. This angle is going to be parallel to that conveyor. It's going to be 15 degrees from horizontal. Now, again, if it's coming in this direction, I can move it anywhere along its line of action. So I'm going to start its tail here, and we're going to show it going up and to the left in that third quadrant, okay? So again, it's actually pushing from the bottom going up here, but we're going to push it right along that line of action, and its tail is going to start at the origin or the center of gravity, and this is going to be our F. And then we know this to be 15 degrees. The last one is going to be our support force, okay? Our support force, again, is technically at the bottom of the block, but we're going to push it along its line of action. Its tail is going to start at that center of gravity, and it's going to go up and to the right. Okay. Tyler, do you have a question?
I was just going to mention the F force. We don't know the degree for it.
We don't. Oh, yeah, we do. 15.
No,
it's going to be
this
15.
Force. That's for this force.
It's going to be for this one too. Okay. So this is going to be P. Now, this is perpendicular. So this angle right here is going to be 15 degrees.
Oh, okay, now.
Yep. Yep. Okay. So again, on the block itself, P is coming up, like kind of pushing up at the bottom of it. But again, we can move that along its line of action so that coming from the center, which would be the center of gravity of that block, all of the forces, tails are there and pulling away, okay? This is also called, and I didn't emphasize this the last time, but when we were in module, or when we were in module 2, whenever we have forces, a force system that shares the same point of application, or when we push the forces along their line of action, they share a common point where they intersect. That's called a concurrent force system, okay? So this is a concurrent force system. They share a common point. All right, so any questions so far? So this does look a little different, right, than what we ended up with, but we're going to see that that's going to be something that we do quite often is we push these forces along their lines of action so that we can end up with that common point. All right, so now as we look here, what do you think our next step is going to be? Is there anything we can solve for right now? We can solve for W. Let's find what the magnitude of W is, right? So we know that weight is equal to mass times gravity, right? And in this case, our mass, it told us, was 30 kilograms, and gravity is 9.81 meters per second squared. Put the units in all phases of the problem. I don't want to see 30 and 9.81 by itself. That's points off. Now, when I have a kilogram meter per second squared, is there a shortened version of that? It's called a what? See, I was a physics teacher in my prior life. It's called a what?
A Newton.
A Newton. That's right. It's a Newton. So we're not going to put kilogram meters per second squared. We're going to put 30 times 9.81, which it looks like is 294 newtons. Okay. So we can say 294 newtons. Yeah, the last school that I taught it, I also taught physics, so it was fun. I don't get to do that here. So when I can do it, Okay, so now we have that. Can we solve for P or F? No, those are our unknowns. Those we want to know. Actually, the only thing that we want to find, we only need to know F. It's only asking us for F. So we don't even have to find P. But we need it. We need it for our equations of equilibrium. All right, next step. What do you think we're going to do? Do we have any forces that are not on the X and Y axis? Yep. So what do we need to do with those? Starts with a C. Virtually, if you guys want to chime in, you can either put it in the chat box or let me know. What are we going to do next? What's our step number 3? Starts with a C, ends with onents.
Calculate the components.
Calculate the components, exactly. So we're going to do components next. So before we can do the calculations, we got to show them on our diagram, right? So go ahead and show your PX, your PY, your FX, and your FY. Let's see here. I could have gone a little bit larger. Because now my 15 degrees is PY. So now we can go ahead and we can calculate our components for PX and PY and FX and FY. So I'm going to start with P. PX is going to be equal to, when we look at our triangle up here, we know this angle right here is 15 degrees. So for the X component, it would be the equivalent side opposite. So it would be the sine of 15 degrees or the cosine of 75, okay, times P. Okay, so my PX is going to be 0.2588P. And then my PY is going to be the cosine of 15 or the sine of 75 times P. And then you want to do the same thing for FX and FY. This one is going to be the cosine of 15 degrees times F. Oh, it's just the opposite, isn't it? 9F. And FY is going to be the sine of 15 degrees times F. Okay. Now we have our forces, all forces are on the X and Y axes. So now we can use our equations of equilibrium. Some of the forces in the X equals 0, some of the forces in the Y equals 0, and see what we have, okay? So the next thing we're going to do is step number 4. It's going to be our equations of equilibrium. Okay. Whether you start with some of the forces in the X or some of the, and I always start with some of the forces in the X or some of the forces in the Y, does not matter. Okay, it doesn't matter. But you have to tell me you're going to do it. So sum the forces in the X direction is equal to. So no other version of that except capital sigma, capital F sub X is equal to 0. Don't just stop with, sometimes I have students that stop with some of the forces in the X and they don't do equal to 0. Points off. This is an equation of equilibrium, equal sign, two sides. Okay. You're probably like, yeah, I get it. But mark my words. There'll be someone who forgets. That's okay. That's why we do it. Okay, so we're going to write our equation of equilibrium, summing our forces on the x-axis. So that means we have a negative fx because it's pointing to the left, and we have a positive px because it's pointing to the right. And we set that equal to 0. So the left-hand side of our equation is summing the forces in the x direction. Signs are based on our convention. Okay. And now we're going to expand that out for what we found here. So we've got a negative 0.258. Oh, shoots. See, that's why I don't like pencil. Okay, I'm going to put the P first because that's the same number. And then minus, because it's the FX, is going to be 0.9659F. There we go. So I just switched these because I started with the wrong one. And then equal to 0. So we have one equation with two unknowns. We can't solve this, but we're going to put a little cloud around it, and we're going to kind of come back to it if we can. All right, the next thing I'm going to try to squeeze it in right here so that they're next to each other. The next one we're going to do is we're going to do our sum of our forces in our y equals 0. Okay, so now we're going to go back up here and we're going to look just vertically. That means we have a positive Fy, a positive Py, and a negative 294 newtons. Okay, don't forget that one. And remember, set it equal to 0 and don't forget to put your units with your 294. Okay, so make sure the newtons are there. And then now we're going to substitute for each one of these. So 0.9659P plus 0.2588F. And I'm going to put my 294 to the other side right away. 294 newtons. Here again, I've got two unknowns. I've got P and F as the variables that I don't know. So I need to leave that equation there. But this is the second equation that I have that has the same two unknowns. So I'm going to call this one number 1 on the left-hand side, and this one number 2 on the right-hand side. Guess what we're going to do next? We get to substitute. Connor, don't look so excited. You get to do it. You don't have to. You get to. Totally different way of looking at it. All right. So, I guess I'm gonna look at these. Is there anyone that we want to start with, number 1 or number 2, that you feel like it's easier to work with? 1, because there's one less number to deal with, right? Otherwise, it's really not complicated. But yeah, might as well use number 1 first. So I'm just going to rewrite it on my next page here. Number 1 is 0.2588P minus 0.9659F. If you have room where you're doing whatever you're doing, you can just continue on. I just was at the bottom of my page. So now I'm going to solve for one of these variables in terms of the other. Since I've got a negative 0.9959 on the, or negative 0.9659, I'm going to put that right on the other side. So 0.2588P is equal to 0.9659F. Solving for P just because it's on the left-hand side, you could very well solve for F if you wanted to. 0.2588, my P. Would be 3.7322F. Do I get that same number? Okay. And then now we're going to substitute. We're going to go to equation number 2. Okay. And anywhere I see a P, instead of writing P, I'm going to write 3.7322F. So right away, I've got a 0.9659. Here's a P. So I'm going to put 3.7322F. So that goes right there. Okay, because that was what P was in the previous number 2. Plus 0.2588F is equal to 294. N is just newtons. It's not a variable. So I've got F as my only unknown now in this problem. I do need to multiply that out. So I've got 0.9659. Then I can combine these two. And I get 3.8637 F is equal to 294 newtons. And now solving for F. .1 newtons. Okay. Now, we don't need to solve for the angle here because we showed F at a 15-degree angle here when we did it. If you wanted to put the at 15 degrees, that's totally fine, but it's identified and that was based on our original illustration. Now, you could go back and solve for P, but the problem just wants to know what F is, okay? It just wants to know what is the force that is keeping it up so that it stays right where it's at on that conveyor. So we can stop here. But again, if you're curious and you're like, I'd really like to know what P is, you could solve for it if you want, but you don't have to. Okay. Any questions on problem number 2.5? So we started out by drawing our free body diagram, pushing our forces along their lines of action so that we could have them all come from the center of gravity of that block. Then we solved for the weight, broke forces into components that weren't on the X and Y axis, used our equations of equilibrium, but we found that we had two equations with the same two unknowns, and then we did substitution to solve for F. Okay. So I'm going to stop